Welcome! Today, we'll be diving into LeetCode problem number 2145, count the hidden sequences. This problem challenges us to calculate the number of valid hidden sequences based on a given differences array in specific bounds. Let's explore the problem and its solution step by step. In this problem, we're tasked with finding the number of valid hidden sequences that can be formed from a given array of differences and a specified range. The array, called differences, represents the difference between consecutive elements in the hidden sequence. For example, if the difference between two consecutive elements is given as 2, it means the next element in the sequence is 2 greater than the current one. Along with this, we are provided two integers, lower and upper, which define the inclusive range within which every element of the sequence must lie. A sequence is considered valid only if all its elements are within this range. Our goal is to calculate how many such valid sequences can be constructed. If no valid sequence exists, we simply return 0. Let's look at the first example to understand this better. Here, we're given differences equals 1, minus 3, 4, lower equals 1, and upper equals 6. To form a valid sequence, we start with an initial value, _0, which can be freely chosen. From there, we calculate the subsequent elements of the sequence by applying the differences. For instance, if we choose _0 equals 2, the sequence becomes 2, 3, 0, 4, which is valid because all its elements lie within the range 1, 6. Similarly, if _0 equals 3, the sequence becomes 3, 4, 1, 5, which is also valid. However, if we pick _0 equals 5, the sequence becomes 5, 6, 3, 7, which is not valid because 7 exceeds the upper bound of 6. After trying all possible starting points, we find that only 2 valid sequences can be formed. Now consider the second example where differences equals 3, minus 4, 5, 1, lower equals 1, and upper equals 10. Starting with a freely chosen _0, we calculate the sequence step by step using the differences. For instance, if _0 equals 1, the sequence becomes 1, 4, 0, 5, 6. Here, every element lies within the range 1, 10, so this sequence is valid. Similarly, if _0 equals 2, the sequence becomes 2, 5, 1, 6, 7, which is also valid. Trying other values, such as _0 equals 3 or _0 equals 4, results in additional valid sequences like 3, 6, 2, 7, 8, and 4, 7, 3, 8, 9. However, choosing _0 equals 5 makes the sequence 5, 8, 4, 9, 10, which includes an element equal to 10, the upper bound, but remains valid. Beyond this, if we increase _0 further, the sequence exceeds the range. After counting all possible valid sequences, we find that there are 4 in total. To summarize, in the second example, there are exactly 4 valid hidden sequences. Now let's examine the constraints of the problem. The length of the differences array can go up to 100,000, meaning our solution needs to be efficient to handle large inputs. Each difference in the range bounds, lower and upper, can vary between -10,000 and 10,000. Importantly, the first element of the hidden sequence, _0, is not fixed and can be chosen freely, as long as all resulting elements remain within the specified range. This means that the key to solving the problem is determining the valid range of _0 that keeps the entire sequence within lower, upper. To do this, we may need to calculate the cumulative minimum and maximum values of the sequence based on the differences. An efficient approach will ensure we handle the constraints while accurately counting the valid sequences. To solve the problem of counting hidden sequences, we start by understanding the requirements. We need to determine how many valid sequences can be formed based on the given differences array and the bounds, lower, upper. Initially, we can consider a brute force approach, which is straightforward but inefficient. Here's how it works: we start the sequence with an arbitrary value, such as the lower bound, and generate the rest of the sequence using the provided differences. For each sequence, we ensure that all its elements fall within the specified bounds. This means iterating through all possible starting values within the range, lower, upper, generating sequences, and checking their validity. However, this approach becomes computationally expensive as the range of bounds increases or as the differences array grows longer. The time complexity, being proportional to the product of the range size and the array length, makes this method unsuitable for larger inputs. While intuitive, this approach highlights the need for a more efficient solution. Now, let's explore an optimized approach that addresses the inefficiencies of brute force. The key insight is that the entire sequence is uniquely determined by its starting value, a_0. To ensure validity, we focus on the cumulative impact of the differences array, which can be captured using a prefix sum. By calculating the cumulative sum of the differences, we can determine the minimum and maximum offsets that the sequence can take relative to its starting value. Specifically, the smallest value in the sequence will be a_0 plus min, prefix _sum, and the largest will be a_0 plus max, prefix _sum. For the sequence to remain valid within the bounds, these values must satisfy the inequalities, lower equals a_0 plus min, prefix _sum, and a_0 plus max, prefix _sum, equals upper. Rearranging these gives us a valid range for a_0, which is lower min, prefix _sum, to upper max, prefix _sum. Once we compute this range, the task reduces to counting the integer values within it, which can be done directly using a simple formula. This eliminates the need to explicitly generate sequences, making the approach far more efficient. The optimized approach has a time complexity of O(n), where n is the length of the differences array. This efficiency comes from the two main steps: calculating the prefix sum, which is linear in complexity, and determining the range of valid starting values, which is a constant time operation. This makes the method scalable even for large inputs. The key advantages of this approach include its efficiency and the fact that it avoids explicitly generating sequences, focusing instead on deriving the valid range for a_0. However, it does require a good understanding of mathematical concepts like prefix sums and inequalities. These are essential for correctly implementing the solution. By shifting the focus from brute force simulation to analytical reasoning, this method provides a much faster and more practical way to solve the problem. The chosen strategy for solving this problem is the optimized approach due to its significant efficiency and scalability compared to brute force. By leveraging prefix sums and deriving the valid range for the starting value mathematically, we eliminate redundant computations and achieve a linear time solution. This is particularly crucial given the problem's constraints, where both the input size and the range of bounds can be large. While the brute force method is more intuitive, its inefficiency makes it impractical for real-world use cases. The optimized solution, on the other hand, strikes the perfect balance between clarity and performance. It reduces the problem to analyzing bounds mathematically, avoiding the overhead of generating sequences explicitly. In summary, this approach is not only the most practical but also the most performant choice for solving problem number 2145. In this problem, we are tasked with counting the number of valid hidden sequences that can be derived from a given differences array, while adhering to specific bounds. The sequence begins with an initial value, hidden 0, that must lie within the range of lower and upper. From there, each subsequent element is calculated by adding the corresponding value from the differences array to the previous element. The challenge lies in ensuring that every element in the sequence remains within the bounds of lower and upper. The goal is to determine how many valid sequences can be generated under these constraints. To solve this, we need to evaluate the constraints on the sequence and determine the possible values for the initial element, hidden 0. This can be done efficiently by leveraging a prefix sum approach to compute the cumulative changes in the sequence. Let's break the algorithm into clear, actionable steps. First, we iterate through the differences array to calculate the cumulative changes in the sequence. By initializing a variable cumulative to 0 and updating it iteratively as we traverse the array, we can track how the sequence evolves relative to the initial value, hidden 0. Along the way, we also keep track of the maximum and minimum cumulative values encountered, referred to as max_cumulative and min_cumulative. These values are critical because they determine the range of valid values that hidden 0 can take. Once we have these cumulative bounds, we can calculate the range for hidden 0 that ensures the entire sequence stays within the limits of lower and upper. Rearranging the constraints leads us to the equation lower min_cumulative being the lower bound for hidden 0 and upper max_cumulative being the upper bound. These calculations allow us to identify the valid range for the initial value. From this range, we can count the possible values for hidden 0. If the lower bound, start, is less than or equal to the upper bound, end, the number of possible values is simply the size of the range, calculated as end, start plus 1. If the range is invalid, meaning start is greater than end, then there are no possible values for hidden 0, and we return 0. The final step is to return the count of valid initial values, which directly corresponds to the number of valid hidden sequences. By focusing on the constraints of hidden 0, we simplify what initially seems like a complex problem into a straightforward calculation. This approach avoids the need to generate and verify all possible sequences, making it both elegant and efficient. The key insights behind this algorithm revolve around efficiency and simplicity. By using a prefix sum approach, we reduce the problem to analyzing how the cumulative changes affect the range of hidden 0. Instead of evaluating each possible sequence, we focus on calculating the range for the first element based on the cumulative bounds. This insight allows us to sidestep unnecessary computations and solve the problem in linear time. Additionally, the algorithm's space efficiency is notable, as it relies only on a few variables, such as cumulative, min_cumulative, and max_cumulative, to track the state. This ensures that the solution is both time and space optimal. The algorithm is robust and handles the problem's constraints with precision, making it a powerful tool for tackling this type of sequence-based problem. Finally, let's analyze the computational complexity. The time complexity of the algorithm is O(n), where n is the length of the differences array. This is because we iterate through the array once, performing constant time operations at each step. The space complexity is O(1), as the algorithm only uses a fixed number of variables to track the cumulative sum and bounds. These characteristics make the solution highly efficient, even for large input sizes. For edge cases, the algorithm gracefully handles scenarios such as an empty differences array, where all values of hidden 0 within the bounds are valid. It also accounts for invalid bounds or situations where the cumulative sum forces the sequence out of range, ensuring that the correct result is returned in all cases. This combination of efficiency, clarity, and robustness makes the algorithm an ideal solution for this problem. The provided code solves LeetCode problem number 2145, Count the Hidden Sequences, which involves calculating the number of valid hidden sequences based on the differences array in bounds lower and upper. First, the prefix _sum is initialized to 0. This represents the cumulative sum of the differences, which helps reconstruct the hidden sequence. Two variables, min_hidden and max_hidden, are also initialized to 0. These variables will track the smallest and largest values of the prefix sums as we process the differences array. The loop iterates through the differences array, updating prefix _sum by adding each difference. At each step, min_hidden is updated to the smaller of its current value or the current prefix _sum, while max_hidden is updated to the larger value. This ensures we capture the full range of possible values the hidden sequence can take. After the loop, the range of prefix sums, range_width, is calculated as max_hidden min_hidden. This determines how much the hidden sequence can vary based on the differences array. Next, the maximum and minimum starting values for the sequence are determined. The maximum start, max_start, is calculated as upper range_width, ensuring the sequence stays within the upper bound. The minimum start is simply lower, as the sequence must also respect the lower bound. Finally, the total number of valid starting points is calculated as max 0, max_start, min_start plus 1. This ensures that the result is non-negative, as there may be no valid sequences if the range is too restrictive. The function returns this value, representing the total number of valid hidden sequences. This is the Java implementation of the Count the Hidden Sequences problem. The solution mirrors the Python logic, leveraging Java-specific constructs such as the math.min and math.max functions for range calculations. Variables are explicitly typed, and the method's signature adheres to Java conventions. The code calculates the range of prefix sums and determines the count of valid sequences using the given constraints. In this example, we have a small range with simple differences. The input differences are 1, -2, 1, and the bounds are 3 and 6. To begin, we initialize some variables, prefix underscore sum is 0, and both min underscore hidden and max underscore hidden is 0. Next, we calculate the range of prefix sums by iterating through the differences. For the first difference, 1, we add it to prefix underscore sum, resulting in 1. This updates our max underscore hidden to 1, while min underscore hidden remains 0. For the second difference, minus 2, we subtract 2 from the prefix underscore sum, giving us minus 1. This updates min underscore hidden to minus 1 while max underscore hidden stays at 1. Finally, for the last difference, 1, we add it to prefix underscore sum, bringing it back to 0. In this case, min underscore hidden and max underscore hidden remain unchanged. The final values are min underscore hidden as minus 1 and max underscore hidden as 1. Now that we have the range of prefix sums, we calculate the total range width by subtracting min underscore hidden from max underscore hidden. This gives 1 minus 1, which is 2. Next, we determine the bounds for valid starting points. The max underscore start is calculated as upper minus range underscore width, which is 6 to 2, resulting in 4. The min underscore start simply equals the lower bound, which is 3. To count the valid starting points, we use the formula max, 0, max underscore start, min underscore start plus 1. Substituting the values, we get max, 0, 4 to 3 plus 1, which equals 2. Thus, the final output for this example is 2. In this next example, we work with a larger range and include negative differences. The input differences are -3, 2, -1, 4, and the bounds are -5 and 5. Again, we start by initializing prefix underscore sum, min underscore hidden, and max underscore hidden is 0. We then proceed with calculating the range of prefix sums. For the first difference, -3, prefix underscore sum becomes -3, updating min underscore hidden to -3 while max underscore hidden remains 0. The second difference, 2, adds to prefix underscore sum, resulting in -1, but there's no change to min underscore hidden or max underscore hidden. For the third difference, -1, prefix underscore sum becomes -2, which doesn't change the range since min underscore hidden is still -3 and max underscore hidden is 0. Finally, the fourth difference, 4, brings prefix underscore sum to 2, updating max underscore hidden to 2. The final values are min underscore hidden is -3 and max underscore hidden is 2. With the range of prefix sums calculated, we determine the total range width by subtracting min underscore hidden from max underscore hidden. This gives 2 minus 3, which equals 5. To calculate the bounds for valid starting points, max underscore start is upper minus range underscore width, or 5 to 5, which equals 0. Min underscore start is simply the lower bound, -5. Using the formula max, 0, max underscore start, min underscore start plus 1, we substitute the values to get max, 0, 0, -5, plus 1, resulting in 6. Therefore, the final output for this example is 6. In this example, we analyze a case where no valid sequence exists. The input differences are 4, -2, 3, and the bounds are 1 and 2. Starting with initialization, we set prefix underscore sum, min underscore hidden, and max underscore hidden to 0. Then, we compute the range of prefix sums. For the first difference, 4, we add it to prefix underscore sum, making it 4, and update max underscore hidden to 4 while min underscore hidden stays at 0. The second difference, -2, reduces prefix underscore sum to 2, but the range remains unchanged. Finally, the third difference, 3, increases prefix underscore sum to 5, updating max underscore hidden to 5. The final values are min underscore hidden is 0 and max underscore hidden is 5. To find the total range width, we subtract min underscore hidden from max underscore hidden, resulting in 5 to 0, which is 5. Next, we calculate the bounds for valid starting points. Max underscore start is upper minus range underscore width, which is 2 to 5, giving -3. Min underscore start equals the lower bound, 1. Using the formula max, 0, max underscore start, min underscore start plus 1, we compute max, 0, -3 to 1 plus 1, which equals 0. This means there are no valid starting points, and the final output for this example is 0. To analyze the time complexity of this solution, we start by looking at the main operations involved. The first step is the prefix sum calculation. Here, we iterate through the differences array, which has a length of n. During each iteration, we update the prefix _sum and use the min and max functions to track the smallest and largest values encountered. Both of these are constant time operations, so the time complexity of the loop itself is O, n. After completing the loop, the next step is to calculate the range width, which is simply the difference between max_hidden and min_hidden. This is a straightforward arithmetic operation that takes constant time, or O1. Finally, we compute the number of valid starting points for the hidden sequence. This also involves a few arithmetic operations, such as subtraction and the use of the max function, all of which are O1. When we combine these steps, the overall time complexity of the solution is O(n), where n is the length of the differences array. Now, let's consider the space complexity of the solution. The algorithm primarily relies on a handful of variables to track intermediate values during the computation. These include prefix _sum, which stores the running sum as we iterate through the array, and min_hidden and max_hidden, which keep track of the minimum and maximum values of the prefix sum. Additionally, variables such as range_width, max_start, and min_start are used in the final calculations to determine the number of valid sequences. Since none of these variables depend on the size of the input and no additional data structures or recursive calls are introduced, the space usage remains constant. Therefore, the space complexity of the solution is O1, making it highly efficient in terms of memory usage. To understand the efficiency of this optimized approach, it's helpful to compare it with a naive solution. A brute force method would involve generating all possible sequences that fall within the bounds defined by lower and upper. This means iterating through every potential starting value for the hidden sequence, which could take up to upper-lower iterations. For each starting value, we would then construct the sequence by applying the differences array, which requires O(n) time. After constructing the sequence, we would verify its validity, which is another O(n) operation. Combining these steps, the time complexity of the naive approach would be O(upper-lower**n), which becomes extremely inefficient for large ranges between lower and upper. In contrast, the optimized solution bypasses the need to generate or validate individual sequences. By focusing on mathematical reasoning and prefix sum calculations, it achieves a time complexity of O(n) and a space complexity of O1. This makes it significantly more scalable, especially when the input size or range is large. When solving this problem, there are a few common mistakes that can trip you up. First, one of the most frequent errors is incorrectly handling the bounds. Many assume that the lower and upper bounds apply to each individual element in the sequence, but that's not the case. The bounds actually constrain the entire cumulative sequence, not the individual differences. Misunderstanding this can lead to incorrect calculations when determining valid ranges. Another mistake is ignoring the use of prefix sums. Attempting to reconstruct the sequence directly without leveraging prefix sums makes the problem unnecessarily complex. The prefix sum approach simplifies things by reducing the problem to cumulative sums and their bounds, allowing for efficient computations. Finally, off-by-one errors in range calculations are another common pitfall. This happens when you miscompute the range of valid starting values, such as including invalid endpoints or missing edge cases. These small mistakes can lead to overcounting or undercounting the valid sequences, so precision is critical here. Now, let's look at a couple more mistakes that are worth avoiding. Overcomplicating the problem is a big one. Some solutions use nested loops or attempt to generate all possible sequences explicitly. This approach leads to exponential or quadratic time complexity, which is inefficient and won't scale for large inputs. Instead, the problem can be solved much more efficiently by focusing on the prefix sum approach. Another major issue is ignoring edge cases. For example, you should consider scenarios where the differences array is empty, where lower equals upper, or where the bounds are extremely tight. Overlooking these situations can result in incorrect outputs or even runtime errors. Testing edge cases thoroughly ensures that your solution is robust and handles all possible inputs. To perform well in an interview setting, it's important to recognize the key insights for this problem. Identifying the prefix sum pattern is crucial since many sequence-related problems rely on cumulative sums. Being able to spot this quickly demonstrates strong problem-solving skills. Simplifying the problem to finding valid starting points within the bounds highlights your ability to break down complex challenges. Efficiency is another major focus for interviews, aiming for O and time complexity by iterating through the differences array once is the optimal approach. Avoid brute force solutions, as they indicate a lack of understanding of the problem's constraints. Additionally, clarity in explanation is key. Be prepared to explain why the prefix sum method works and how it satisfies the constraints. Finally, showing awareness of edge cases during your explanation can leave a strong impression, as it demonstrates thoroughness and attention to detail. This problem also connects to several related problems on LeetCode, which can help deepen your understanding of similar concepts. For example, LeetCode 238, product of array except self, involves cumulative products or sums and their ranges. Another related problem is LeetCode 862, shortest subarray with sum at least k, which also leverages prefix sums and bounding values. LeetCode 152, maximum product subarray, involves dynamically tracking cumulative values and their bounds, while LeetCode 325, maximum size subarray sum equals k, focuses on finding valid ranges using prefix sums. Practicing these problems can help reinforce the techniques used in this problem and build your confidence in tackling variations. There are alternative approaches to solving this problem, though each comes with its own trade-offs. The brute force approach involves generating all possible sequences based on the differences array and counting those that fall within the bounds. However, this method has exponential time complexity, 2 to the power of n, making it impractical for large inputs. It's only useful for understanding the problem on a small scale. Another option is the two-pass solution. In this approach, the first pass computes the prefix sums, and the second pass determines the valid range of starting values. While this method achieves O and time complexity, it uses slightly more memory and is less concise than a single-pass solution. Finally, the sliding window technique dynamically adjusts the range of valid starting values as you iterate through the array. While this method can be useful for problems with additional constraints, like requiring a minimum sequence length, it is overly complex for this specific problem. To summarize, the prefix sum approach is the most efficient and elegant way to solve this problem. By reducing the task to simple range calculations, it avoids unnecessary complexity and ensures that all constraints are satisfied. The key is to derive the maximum and minimum cumulative sums, which help determine the range of valid starting points. Testing edge cases, such as tight bounds or empty inputs, ensures your solution is robust and reliable, which interviewers will appreciate. In terms of complexity, this approach achieves O and time complexity, as it involves a single pass through the differences array. Additionally, it uses O1 space, as we only need to track cumulative sums and bounds. By focusing on these insights and maintaining efficiency, you can deliver a solution that is both optimal and clear. Great job! In summary, we use prefix sums to efficiently solve the problem within O and time. Remember, understanding constraints and leveraging the right algorithm is key. Thank you for watching and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!